go. The thing shows up as a rainbow, but and it was tripping me out, but I got used to it. But yeah, okay. Well, yeah, it's a happy Friday. It's week 7 Friday. We're just a few weeks away from the end of the quarter. I hope you've enjoyed the class so far. Today we're going to look at numeric optimization, and we're going to look at this method called golden section search. So golden section search is a numeric method. Doesn't involve derivatives. Doesn't involve it's kind of like bisection method. Bisection method we used for root finding to find where the function is equal to 0. And golden section search is going to be used to find a local minimum. And you can inverse the function, multiply by -1 to get, and not the inverse, but you multiply by -1 if you want to find a local maximum or something. But we can use golden section search to find a minimum, and it's based off of the golden ratio. And so the golden ratio is one of these numbers that seems to show up all over the place. I think there's a lot of, I don't know, you'll watch like some video on YouTube about like how beautiful math is and how it shows up in nature. And it always kind of shows like, I think the most common things are like the nautilus shell, the sunflower seeds, I don't know what else, Fibonacci numbers, acorns, or not acorns, pine cones and stuff. And you kind of see these spirals, and these spirals are supposed to be representations of the golden ratio, because you can kind of trace out the spiral and the thing. And anyway, the idea behind the golden ratio is, here is this rectangle, and in the rectangle I've drawn a square. And so this square has a side of 1 on this side and a side of 1 here, and the length of this rectangle is 1 plus x. And the idea behind the golden ratio is that if you were to cut off a square here and you're left with a rectangle over here, this rectangle over here has the same ratios as the larger rectangle. Okay, so that is to say, if I draw the original large rectangle had one side with a length of 1 and one side with a length of 1 plus x, this smaller rectangle, the long side has a length of 1 and the short side has a length of x. Okay, so if you take a look at these arrows, the length of the short side, 1 to the length of the long side, red, and 1 to 1 plus x, is the same ratio as the length of the short side, which is in blue here, x, to the length of the long side, 1. Okay, so we're going to say blue to the red, 1 to 1 plus x, is the same ratio as blue to red over here, which is going to be x to 1. So that is, if you remove this square over here, this rectangle over here has the same proportion, same relative size of the length and width as the larger one. So with this, we can solve for what x should be. So I got 1 over 1 plus x is equal to x, and we just use a little bit of algebra, multiply both sides by 1 plus x, subtract 1 from both sides, I got x squared plus x minus 1. We're going to solve for x using the quadratic formula. Sorry, I don't know why my audio keeps cutting in and out. We can say x is -1 plus or minus 5 divided by 2. And if we look at this, x is a positive value, so we're going to go with the plus 5. Okay, so we get -1 plus the square root of 5 over 2, and that's approximately 0.618. Okay, it's a irrational number, but we're going to say it's approximately 0.618, and this is about my golden ratio. And so some neat little features of this is if I do 1 divided by 1.618, that gives me 0.618. So 1 over 1 plus x is the same as x. So I get 0.618, 1.618, and 0.618 here. And then another feature of this is that you can kind of rearrange things, and 1 minus x is the same as x squared. So if you do 1 minus 0.618 and you get 0.382, that's the same as 0.618 squared. Will also give you 0.382. So both of these things. So this works out nicely. Okay, so let's apply this knowledge from the golden ratio, and we can create a search algorithm. And we call this golden section search. We've got a search algorithm that uses the golden ratio to do this. So here we're just going to find the minimum of this very, very simple function. It's a parabola x squared minus 0.8x. So I can tell you the minimum happens at 0.4. Okay, and we can kind of see this. See this already. But what we'll do is we'll use golden section search to search for this. And so the way it works is we have to start off with just some arbitrary interval, and we have to assume that a minimum value exists somewhere between the lower and upper endpoints of the interval. So we've got a lower bound, we've got an upper bound, and we're going to say there's a minimum somewhere between the lower and upper bound. So here I'm going to say the lower bound is 0, the upper bound is 1, and yeah, is there a minimum somewhere between 0 and 1? We're just going to assume yes. Okay. Now, for teaching purposes, I've graphed out the entire function. Okay. But when you are running this algorithm, generally, you won't know what the function looks like here. You're just going to have, you might evaluate the function at a couple points, but you're not necessarily going to know what the function itself looks like. For teaching here, I've drawn out the function, but all we're going to just say is, there's some function, we're assuming there's a minimum, but you don't necessarily know what the function looks like in there. Okay, so what I'm going to do is we're going to call 0 our lower bound, 1 my upper bound, and we're going to look at 2 internal points within the interval. Okay, the 2 inner points, we're going to use the golden ratio. So if I say the golden ratio is around 0.618, I'm going to go around 0.618 of the way, so around 62% of the way from the lower bound to the upper bound. And that's going to form kind of my first internal point. And then I'm going to start at the upper bound and go around 62.618 of the way to the lower bound, and that's going to form my second inner point. Okay, so this point x1, my first inner point, is going to be the lower bound plus phi, or 0.618, times the distance between u and L, okay, the upper and the lower. So I'm going around 62% of the way from the lower bound to the upper bound. And then here, if I go from the upper to the lower bound, I'm going to go 62% of the way from the upper bound to the lower bound, so I'm going to do u minus phi times u minus L. All right, is that okay? So for my first interval, I chose very simple numbers. I chose 0 and 1, and so my inner point x1 is going to be at 0.618, and my inner point x2 is going to be 1 minus 0.618, like 0.382. So it's going to be here at 0.382 and 0.618. Okay, and what I do is I evaluate the function at these 2 inner points. I evaluate the function at x1, I evaluate the function at x2. And what I find is that the value of the function at x1 is greater than the value of the function at x2. Okay, and again, when we're doing this, we don't actually know what the function looks like inside the interval, but we do know the function at x1 is larger than the function at x2. And so the reasoning here is going to be, so what we know is start our original interval from 0 to 1, there's at least one minimum point there. There's a minimum value. And once we find that x2 is less than x1, we can throw away all the points to the right of x1. I can say I don't have to search there anymore for a lower point because I know a lower point exists to the left of x1. Okay, I can say I'm looking for a minimum value, and so I know that to the left of x1 there's at least there's a point that exists that's lower than f of x1, and that's at x2. So I'm not even going to bother searching anything to the right of x1 because I know there's already a point less than x1 to the left, f of x1 on the left, and it's on the left-hand side, so we're just going to search the left-hand side. So we're going to throw everything away on the right-hand side. We're going to just throw this side away, okay? And now I'm going to just search on this side. I'm going to search from 0 to 0.618. Okay, so this is now going to be my new bounds of the interval. So I'm going to keep my lower bound at 0. My upper bound is now at x1, 0.618. Okay, and we're going to continue our search here. Okay, and this is where the beauty of the golden ratio comes in. What I can do is I want to find two internal points. I want to find a point that's 0.618 of the way up to x1, and I want to find a point that's 0.618 of the way from x1 down to 0. Okay, what is the point that's 0.618 of the way from 0 to 0.618? It's going to be 0.618 squared, and that's this location x2. Okay, because of the golden ratio, this point is at 0.382. Okay, the point, so x2 is located at 0.618 of the way down from 1 to 0, which is equivalent to being 0.618 of the way from 0 to 0.618. Okay, so back here we said this thing 1 minus x, which is 0.382, is equivalent to x squared, which is 0.618 squared. So if I'm saying I'm going from 0 to 0.618 and I want to go, basically 62% of the way from 0 to here, it's going to take me to right here, which is my location x2. Okay, so that's kind of the cool thing, is that I take my old x1, I'm going to set that to be my new upper bound, and when I'm looking for one of my internal points, which is going to be 0.618 of the way from the lower bound to the new upper bound, that's going to be at the location that I had previously calculated to be x2. All right. So why do we care about this? Why do we care about this? Well, let's say this function. So this is a very simple function, so plugging in numbers is not very hard. But let's say your function is computationally very expensive. Let's say it's like the result of some, infinite series, and maybe you're not going to actually calculate the infinite series, but you're going to say calculate the first 1,000 terms of this series. So what is the value of the function at 0.7? You got to calculate it at 1,000 terms. What's the value of the function at 0.3? And maybe each of these computations take a while to compute, or take a while to calculate. So if you have to, at every iteration, if you have to calculate 2 new values, it might take a while to do. But if you can say at my next iteration, I can just reuse, I've already calculated the value here, and I can just reuse it, and I only have to calculate 1 new value at each iteration, we're effectively reducing the amount of computation we have to do at each interval in half, right? So at each iteration, I only have to calculate 1 new value of the function. I don't have to calculate two new values, 2 internal values. So I'm going to take this old x2 value, I'm going to reuse it, but this is now my new x1. Okay, this is now the x1, and so now I have to calculate a value that's 0.618 of the way from here down to here, and that's going to be over here. Okay, so this is what I have down here, and I calculate the function. Okay, I calculate the function here, and I compare it to this value. So this value I'm just reusing from before. I had already calculated it. I don't need to recalculate it. I'm going to find this new x2 value, which is 0.618 minus 0.618 times 0.618, and this gives me 0.236. I'm going to say, okay, what is this value? I say, okay, it ends up being higher than x1. So using, again, the same logic, saying, well, we know there's a minimum value between the lower and the upper bound, and we know it's not going to be to the left of x2 because we know there's already a point to the right of x2 that's lower. We're going to throw away everything to the left of x2. So I'm going to just eliminate this side over here. Okay, and so this is my new thing. And again, because of the properties of the golden ratio, this the x2 becomes my new lower bound, and what used to be x1, this is going to be my new x2. And now I have to calculate a new value, a new internal value, which is going to be 0.618 of the way from the lower bound to the upper bound. So it's going to be somewhere around here. Okay, so I do that calculation, and here it is. And at this point, I calculate, again, I'm reusing the old values. I calculate this value, I find the blue value is greater than the yellow value. And so because of that, I'm going to throw everything away, throw away everything to the right of x1. x1 will be form my new upper bound. So now I'm going to search from here to here. Okay, so we throw that away. Here's my new, I'm reusing this point. I'm going to calculate this one. So you can see this value gets reused right there. And this is the new value I have to calculate. Okay, so looking at these two internal values, we can see this one on the left is slightly higher than the one on the right. So we're going to throw away the area to the left. And this internal value will get reused. Okay, we can see it gets reused, and we now have to calculate a new internal value here. We compared these two things, and we say, okay, the one on the left is just ever so slightly higher. Maybe it's hard to see. So we're going to throw away everything to the left here. This internal value at this dotted line on the right will get reused. And we calculate a new one. Okay, over here, this side is greater, so we're going to throw that side away. And we can see at each iteration, our interval gets smaller by around 38%. And we just keep running this until we're going to hone in on the actual minimum. So the actual minimum is somewhere around at 0.4, but it takes a little while, but we can keep running it. And I think this is as many iterations that I've graphed, but we can see how it will zero in on the minimum value there. Okay, so golden section search I wrote is very robust in that if a minimum lies within the interval, it will find the minimum. If the minimum is on the boundary of the interval, okay, then it will end up converging to the boundary point. If you've got multiple values inside the interval, then the algorithm is just going to converge to one of the local minimums, okay, one of the local minima. There's different termination conditions. One is you can just take the difference between the upper and lower bound, at least in the x, for x, and say if the difference between x1 and not x1 and x2, but the lower and the upper bound is less than some value, then you can stop. So if it's, if the difference between the lower and the upper is say 10 to the negative 5, 10 to the negative 6, you can stop there. All right, let me go ahead and give you your first view quiz answer. Today's first view quiz answer is D. D as in dog. D as in dog. Okay, and I've coded up, or we have code written for golden section search. This is also posted on Canvas under golden.r. Okay, and so here I think I've written it exactly as I've described, in that it's you give it a function, you give it a lower bound and upper bound, a tolerance level for where to stop. We calculate the golden ratio phi to be like 0.618, so -1 plus square root of 5 over 2. And we're going to find x1 being the lower plus phi times the difference between upper and lower. x2 will be the upper minus phi times upper minus lower. So I get the arrangement of points is lower, x2, x1, upper. We evaluate the function at x1 and x2. And again, our function might be computationally expensive, but we have to evaluate it at these two inner points. And we just run this loop. And it's going to keep running. Our termination condition is if the absolute value between the upper minus lower falls lower than the tolerance, then we will stop. Okay. We've already evaluated the function at x1 and x2. If f2 is greater than f1, Okay, then what we're going to do is we're going to throw away everything to the left of x2. So x2 will become our new lower bound. x1 becomes the new x2. We're going to take f1, which we've already calculated, and that's going to, we're going to assign it to f2. We'll calculate the new value for x1, which will be our new lower bound plus phi times upper minus lower, and then calculate the function at this new x1. Okay, and if f2 is not less than or not greater than f1, if it's the other side, then we flip it around. We'll throw away everything to the right of x1. x1 becomes my new upper bound. x2 becomes the new x1. f2 becomes the new f1. We calculate a new x2 and calculate a new f of x2. And that's it. And we just kind of repeat this over and over and over again. And we'll keep track of the number of iterations. And then at the end, we will tell how many iterations it took to converge. And the value it will report back as far as the value it found will be the midpoint of the lower and upper bounds. So we'll do our lower and upper bounds, divide by 2. That will be the midpoint. Okay, so using our very simple function x squared minus 0.8, where the true minimum is at 0.4. If I used a tolerance of 10 to the negative 5, I get 0.3999999, and it took us 24 iterations to get there. At 10 to the negative 6, it took me 29 iterations to get there. If I wanted 10 to the negative 7, it took me 34 iterations, and at 10 to the negative 8, it took me 39 iterations. Okay, so it seems like every time I want an extra factor of 10 in tolerance, I had to go do an additional 5 iterations. Okay, and the reason for that is if you look at the golden ratio being around 62%, every iteration the interval shrinks, and the next interval is 62% of the size of the previous interval. Okay, and so if you do 62% raised to the 5th power, that's around 9%. Okay, 0.618 raised to the 5th power is around 9%, and so if you run 5 more iterations, the resulting interval will be around 1/9, a little bit less than 1/10. Oh, sorry, not 1/9, 1/11, or a little bit less than 1/10 of the size of the interval, five iterations back. Okay, so that's kind of why we're seeing it shrink, increase. We need another 5 iterations to kind of go down by a factor of 10, approximately. All right, let's take a look at our next topic, which is coordinate descent. Okay, so all of our optimization stuff. So today we saw golden section search, and then in our previous lecture we talked about derivative-based optimization, where you just kind of take a derivative of something and then you apply a root finding method to it. All of those methods are actually fairly simple. They work, and but it's fairly simple to run for a univariate function. Okay, even if you didn't have an optimization algorithm, you could generally find a minimum by just doing what we call a grid search. Okay, a grid search is you just take the function and you evaluate it at a whole bunch of locations, and then you say which one is the smallest, right? And that's effectively what we do when we graph it, right? So the way we graph functions is we just say, like, evaluate the function from, say, 0 to 1 or -1 to 10 or whatever, and then evaluate the function at like 1,000 points, and then connect all of those points with the line, right? That's all we're doing. When you graph a function in R, it doesn't actually understand what the function looks like mathematically. It's just calculating the function at a bunch of points, and then it's just connecting all those points with the line. And so you could just say, hey, what if I go from -3 to +3? Let's increment by a step size of 0.001. So that will give me like 6,000 locations to evaluate. And if it's a simple function, having the computer calculate the function at 6,000 locations might not take very long. And then we ask, which value is the smallest? And it says, oh, the value that was the smallest is the 3,400 first value. And then we say, okay, well, which value of x was that? And then it says, oh, that's where x was 0.4. And that's simple enough, right? So you just evaluate the function at a whole bunch of places, which one's the smallest value, and you got a minimum, right? That didn't even require any algorithm. It just is a kind of a brute force way of getting a minimum. Grid search is kind of this brute force method, and it works, but when you have a multivariate function, it's going to take a long time to complete. Okay, so what if you have a function of two variables, a function of x and y? And so let's say you wanted to evaluate x from -3 to 3, and you wanted to evaluate y from -3 to 3. Okay, and if all of the locations are spaced out by 0.001, you've got basically 6,000 values to evaluate in each direction, and so your entire grid there will have 36 million locations to evaluate. Right? You'd have 0, 0. You'd have 0.001 and 0.001. Oh, I'm sorry, you'd have 0, 0.001, 0, 0.002, 0, 0.003, so on and so forth. And then you'd have 0.001, 0.00, 0.001, 0.001, 0.001, 0.002, and so on and so forth. You'd have 36 million of these places to locate. And then what if you had a function of 3 dimensions? Okay, now you have 36 million times another 6,000, so that's what, 216 billion. Okay, this thing is going to grow very, very big, very, very fast. And so, we don't want to be doing grid search when we have a multivariate function. So this is where we can do coordinate descent. Okay, coordinate descent is an optimization algorithm. And what it does, the way we apply it to a multivariate function is we turn the multivariate function into a univariate function. Okay, so how do we do that? Well, we are going to hold the variables to be a constant except for one variable. So if you have a function of two variables, you hold one of them to be constant. So if you hold y constant, then it just becomes a function of x. Okay. And then, or you hold x constant, and then it just becomes a function of y. Sorry, you have a function of x and y. If you hold one of those things constant, it just becomes a function of one variable. And so what we'll do is we'll do univariate optimization on one variable at a time. So first I'm going to hold y constant, and then I'll find the function. It becomes a function of x, and I find the value of x that minimizes this function. Once I find that value, I'm going to hold the x constant there, and it becomes a function of y, and I find the value of y that minimizes the function. Once I do that, I repeat the process. I hold y constant, find the value of x that minimizes the function, then I hold x constant, I find the value of the function that, hold that thing constant, find the value of the function that minimizes, and so on and so forth. Okay, so I have this little demonstration. I'm excited to show it to you. I don't know how you guys feel about whenever I get excited about something. But let me go ahead and give you your second view quiz answer, which is the letter E. E as in elephant is our second view quiz answer. And I have this code posted on Canvas, but let me go ahead and wipe everything out, and we'll go ahead and do this. So I'm using this library called Plotly, and I'm going to load up the golden section search function from that script golden.r, and this is going to be the function that I want to minimize. The function I want to minimize is going to be x squared minus 2x minus 0.5xy plus 2.5y squared. And let me go to Wolfram Alpha. To show you what this is going to look like. Okay. So the resulting shape is this elliptic paraboloid. An elliptic paraboloid looks like this. Okay, so it's kind of like a bowl. It's like a bowl, except rather than round, it's ellipses. Okay, and the ellipse could be at an angle. Okay, and then it's kind of this shape here, right? And so we want to find the minimum of this shape. This would be a this one's a rectangular elliptical paraboloid. These have the major and minor axes perpendicular to your x and y axis, but it doesn't necessarily have to be that case. Here's one, I think, where it's at an angle, but I don't even know what the equation is there. But okay, it doesn't matter. We're going to try to find the minimum of this thing, and I think, where is the global minimum is at this location, 40 over 39, comma 4 over 39. That's the global minimum of this thing. Okay, but let's come back over here. This is my function. I've shared this code on Canvas. It is intentionally very poorly written, okay? And that's partly because I have you write a coordinate descent thing in your homework, and you'll have to think a little bit better about your solution than what I've done here. So what I've done here is every time I hold a value constant and create a function, I name a whole new function for it, and that's not going to be the system you want to do. You want to kind of have a function where you can kind of get something back where it's not going to be a brand new thing. Okay, so anyway, I can plot this, and so to kind of do this, I will use Plotly, and I will create this plot here. And so on Plotly, this is kind of what it looks like, and so Plotly is this cool thing. Don't use it for your homework. You can use this code and kind of play around with it. But here is the value of the function. So this is from top down. You can kind of see the ellipses. Okay, you can see the ellipses, and the idea here is, we've kind of just cut out this rectangular portion of the ellipsoid. So you see a little bit of the bowl nature of it. Okay, and so our x goes from, say, negative 1.5 to 2, and y is also evaluated from negative 1.5 to 2. And what I'm going to do is I'm going to just start at an arbitrary starting point of negative 1, x at negative 1, and y at 1.5. And that's going to be this dot right here. This yellow dot. It's kind of like a little ball here that is partly covered up by the surface. So this is going to be our starting location. And what we want to do is we want to find the kind of global minimum, which is apparently at 40 over 39, and what was the other one? 4 over 39, something like that. So we want to find kind of this location, which is the bottom of this bowl. So how are we going to do that? What we're going to do is we are going to hold one of the values constant. And so I've got an x and y coordinate. I'm going to just arbitrarily say, let's hold y constant. We're going to hold y constant. Y is currently 1.5. We're going to lock in that value 1.5. And so if I lock in y equal to 1.5, then now it becomes just a function of x. Okay, so my function is just going to become a function of x. I'm going to call this thing function of g at iteration 1. Now again, when you do this, you don't want to create new functions every single time. You want to think of a way where you do create a new function, but you don't have to rename it every single time. So I'm going to go ahead and just hold y constant to be 1.5. Okay, so y is at 1.5, and we're going to hold this constant, and I'm going to add a trace of that line here. Okay, and so so this blue line represents, oops, here I'm holding y constant at 1.5, and so we can kind of see this this parabola, or at least part of it, traced out onto the surface. Okay, and what we want to do is we want to find, holding y constant, now I have just a univariate function, and we're going to ask, where is this function minimized? Okay, this function is going to be minimized somewhere around here. Okay, where is the blue line the lowest? So I'm going to use golden section search to find where the blue line is minimized. And it says it's minimized when x is equal to 1.375. That's where the function is minimized. Okay, so let me just plot where that location is. Okay, so it's minimized at this location at x equal to 1.375. Y is held constant to be 1.5. This is my location. All right, so this blue line is minimized at x equal to 1.375. Okay, now that x is 1.375, I'm going to hold x constant at 1.375, and let me show you what this trace will look like, okay? So if I hold x constant, I'm holding x constant at 1.375, I'm getting this, I guess, purple line, or whatever we want to call this, okay? We're going to hold this, and we're going to find the value that minimizes the purple line, okay? So this is still not the global actual minimum of the two-dimensional function, but it's going to take us to the minimum of the purple. So we can see, the minimum of the purple is going to be somewhere around here, which is not exactly the minimum of the actual value is going to be somewhere up here, but the minimum in purple is a little bit off, but it'll get us closer. Okay, so we're going to find the minimum of this purple line, and we ask, okay, this is now a function of y because I'm holding x constant. So I use golden section search, and I say, hey, what value of y is going to minimize this? So when I do this, it says the function is minimized if you hold x constant at 1.375. It's minimized when y is 0.1375. Okay, 0.1375. What's that? So I'm going to go ahead and add a plot there, or add a point there. And so the minimum of the purple is right here. So that looks about right. Okay. And then we're going to repeat the process. We're going to say, okay, well, let's hold y constant to be 0.1375. We're going to hold y constant to be 0.1375. Let's trace out a line here. Okay. And so here's the green line. And we want to find, okay, where is this green line minimized? And, now we're getting pretty close. We're not quite there, but we're getting pretty close. And we're going to say, okay, let's use golden section search to find where this green line, which is a univariate function, where is that minimized? And that's minimized, right over here. So, now our next iteration is just a little bit different from where we started. Okay, so we started over here, and now we're moving over here. Okay, and we can see we're getting closer and closer to the global minimum. Whoops. Oh, geez. I did something here. Okay, so now we're getting closer to the actual global minimum of our paraboloid surface, the elliptic paraboloid. Okay, and then we would just kind of repeat over and over and over again. So holding one variable, allowing only one variable to be free at a time, we have a univariate function. We have methods for optimizing univariate functions, and we just apply this repeatedly, rather than trying to do all of them all at once. Okay. Is that okay? Does that make sense? Any questions here? All right, let me go ahead and give you your last view quiz answer for today. Today's last view quiz answer is the letter A. A as in apple. A as in apple is your last view quiz answer. Okay, and that's actually all I have planned for you. So we'll call it a day here. Have a good weekend. Enjoy your Monday off. We'll see you on Wednesday.